Start the second major example we're looking at in terms of related rates, and that would be a soap bubble problem, which in this case is a sphere. That's what makes it interesting. So question is, how fast does the radius of a spherical soap bubble change when you blow air into it at a rate of 10 cubic centimeters per second? Again, because we're dealing with a sphere, probably we're going to deal with a three-dimensional idea, and that's what we have right here with our rate given. Cubic inches, cubic centimeters per second is a volume rate. So here's what I know. My dV dt is 10 cubic centimeters per second. They're asking how fast does the radius change, so they're looking for dr dt. And the only variable I have is radius for this sphere. So the natural formula that I should use is volume of a sphere, 4/3 pi r cubed. Take the derivative of this with respect to time, we get dV dt, these are all constants, is equal to, 3 comes out in front, subtract the power, dr dt. Isolate what I'm going to be working with, so clean this up, get dr dt by itself. Here it is. I just kind of flip-flopped. I divided this by 4 pi r squared. And now I just filled it in. dV dt was given as 10. There it is. And I have 4 pi r squared. Now, what they don't tell us is what actually the radius is. If you notice, this is what we define as an open statement. Just how fast does the radius change with no known other numbers given, 10 seconds into it, 5 seconds into it, starting, whatever the case may be. They're just looking for a formula. So if they did perhaps give us when the radius was 8, when the radius was 3 centimeters, etc., then we would go ahead and put 3 and 8 into that. But we don't have to. One thing that is interesting that I want to kind of point out is if you notice the derivative of volume here is 4 pi r squared. That should look familiar as a formula. Secondly, one other bonus thing is, notice as our radius increase from say 1 centimeter to 10 centimeters, if I plug 1 into this, I get this answer. If I plug 10 into this, I get this answer. Notice that the rate at which the radius is increasing from size, the rate actually decreases. Inverse proportion in a sense. Again, that has to more do with that when the bubble gets bigger, even though the radius is getting bigger, the rate at which is decreasing because of the size of the soap bubble. One way to think of it again is to look at it as when you're blowing up a balloon. You may be blowing with the same amount of air, but the way the balloon changes isn't increasing as much, even though the radius is always getting bigger.